Deep beneath the rolling hills and picturesque vineyards along the Franco-Swiss border, buried 100 meters under the earth in a circular concrete tunnel, 27 kilometers in circumference, sits the most complex and ambitious machine ever constructed in human history. It is a machine so colossal that its cryogenic cooling system makes it colder than the deepest voids of outer space, while the microscopic fireballs generated inside its core reach temperatures hundreds of thousands of times hotter than the center of the sun. This engineering marvel is the Large Hadron Collider, or LHC, operated by the European Organization for Nuclear Research, known worldwide as CERN. To the public, the purpose of this gargantuan subterranean ring is often described with a single evocative phrase, smashing atoms. Pop culture and news headlines conjured dramatic imagery of miniature atomic billiard balls hurtling toward each other, shattering on impact into microscopic debris, like porcelain figurines struck by a hammer. But beneath this simplified metaphor lies a reality that is vastly more subtle, astonishing, and counterintuitive. Particle accelerators do not simply shatter existing matter. They transmute pure energy into entirely new forms of reality, recreating the primordial physical conditions that existed just a fraction of a billionth of a second after the Big Bang. To understand how particle accelerators actually work, one must first dismantle the very idea of smashing an atom. In ordinary chemistry and daily life, an atom is a complete, stable structure. If you were to launch two neutral atoms directly at one another in an accelerator, their outer electron clouds would repel each other through the electromagnetic force, or their electrons would be stripped away chaotically, resulting in an uncontrolled and messy collision. Modern high-energy particle physics is not interested in the intact atom. Instead, accelerators like the LHC perform extreme subatomic surgery before the particles ever reach the main ring. They strip atoms down to their absolute bare essentials. For the vast majority of experiments at CERN, the particle of choice is the humble proton, the positively charged heart of the hydrogen nucleus. In specialized runs, scientists also accelerate heavy atomic nuclei, such as lead ions stripped entirely of their 82 orbiting electrons. The entire process begins with an object so ordinary that it defies belief: a small red steel bottle of compressed hydrogen gas, no larger than a household fire extinguisher. A single bottle contains enough hydrogen atoms to supply the Large Hadron Collider with protons for hundreds of millions of years. Because the quantity of matter consumed in high-energy collisions is almost infinitesimally small. Over an entire year of continuous high-intensity beam operations, the LHC consumes less than a single nanogram of hydrogen. To turn this gas into high-energy projectiles, hydrogen is bled in microscopic quantities into a device called a duoplasmatron, or a radiofrequency ion source. Inside this chamber, an intense electric field and an oscillating electromagnetic wave rip the solitary electron away from each hydrogen atom, leaving behind a glowing plasma of bare, positively charged protons. Because these protons carry a net electric charge, they can now be manipulated, pushed, pulled, and steered using the fundamental principles of electromagnetism. You cannot simply dump stationary protons into a 27-kilometer ring and expect them to reach near light speed immediately. If you attempted to inject resting protons into the LHC, the immense magnetic fields of the main ring would bend their path so violently that they would instantly crash into the metal walls of the vacuum chamber. Accelerating subatomic particles is an intricate relay race requiring a cascading chain of progressively larger accelerators, each designed to boost the particles through a specific energy bracket before handing them off to the next stage. The journey begins at Linac 4, a 90-meter-long linear accelerator that uses radiofrequency quadrupoles and accelerating cavity structures to boost the initial bunch of protons from rest up to an energy of 160 megaelectronvolts. In the language of particle physics, an electronvolt is a measure of energy, defined as the amount of kinetic energy gained by a single electron moving across an electric potential difference of 1 volt. While 160 megaelectronvolts might sound modest on a cosmic scale, it means the protons are already traveling at roughly 50% the speed of light. Within the first few meters of their journey, from Linac 4, the beam is injected into the Proton Synchrotron Booster, a 4-ring circular accelerator that squeezes the particles into tighter, denser packets and elevates their energy to 2 gigaelectronvolts, or 2 billion electronvolts. Next, The beam is transferred into the Proton Synchrotron, an historic machine commissioned in 1959 AD that serves as the workhorse of CERN's accelerator complex. The Proton Synchrotron boosts the beam to 26 gigaelectronvolts and performs the critical task of splitting and organizing the protons into tightly spaced packets known as bunches. These bunches are then propelled into the Proton Synchrotron, a circular underground tunnel nearly 7 kilometers in circumference. The Proton Synchrotron ramps the particle bunches up to 450 gigaelectrons, which accelerates the protons to 99.9998% of the speed of light. Only when the particles have reached this staggering velocity are they split into two separate injection lines and funneled in opposite directions into the two twin beam pipes of the main Large Hadron Collider ring. Once inside the primary ring of the LHC, the protons must be accelerated to their final operational energy, 6.8 to 7.0 teraelectronvolts per beam, resulting in a combined collision energy of up to 14 teraelectronvolts. To grasp what acceleration actually means at these extreme regimes, one must turn to Albert Einstein's special theory of relativity, formulated in 1905. In classical Newtonian mechanics, when you apply a steady force to an object, its velocity increases linearly. If you double the energy, the object moves significantly faster. But in relativistic physics, nothing possessing mass can ever equal or exceed the speed of light in a vacuum, which stands as the cosmic speed limit at approximately 300,000 kilometers per second. As a proton is pumped full of kinetic energy inside an accelerator, its speed approaches light speed asymptotically. By the time a proton reaches 450 gigaelectronvolts in the Proton Synchrotron, it is already traveling at 99.9998% the speed of light. When the LHC pumps 16 times more energy into that same proton to bring it to 7 teraelectronvolts, its speed increases only imperceptibly, from 99.9998% to 99.999991% of light speed. In practical terms, the proton is moving so fast that it could circle the entire 27-kilometer circumference of the LHC more than 11,000 times in a single second, because the velocity can barely increase. Where does all that additional pumped energy go? Under the laws of special relativity, the added energy manifests as relativistic momentum and effective inertial mass. At 7 teraelectronvolts, each individual proton behaves as though it is over 7,000 times heavier than its resting mass. Pumping energy into the LHC does not make the particles travel significantly faster. It makes them unimaginably more energetic, packing the kinetic energy of a flying mosquito into a subatomic particle that is 1 trillion times smaller than a grain of sand. The physical mechanism that delivers this immense kinetic boost is the radiofrequency cavity. Situated in a dedicated sector of the LHC ring are 16 hollow, barrel-shaped resonators constructed from high-purity niobium cooled by liquid helium to superconducting temperatures. Inside these cavities, powerful electromagnetic waves are generated at a frequency of 400 megahertz, oscillating 400 million times every second. An RF cavity functions like an invisible, oscillating electric wave. As a bunch of positively charged protons enters the metal chamber, the electric field inside the cavity is timed precisely so that it forms a negative potential ahead of the protons and a positive potential behind them. The negative charge in front pulls the protons forward, while the positive charge behind pushes them, giving the bunch a powerful forward shove. Because the electric field oscillates at high frequencies, the timing must be synchronized with sub-nanosecond precision. If a proton bunch arrives too early or too late, it will experience the wrong phase of the electromagnetic wave, causing it to lose energy rather than gain it. This principle of phase stability acts as a self-correcting mechanism. Protons with slightly lower energy that lag behind arrive during a stronger accelerating field, receiving a larger kick that pushes them forward, while overly energetic protons that race ahead receive a weaker kick. In this way, the RF cavities continuously herd the protons into ultra-tight, synchronized bunches. While electric fields are used exclusively to accelerate particles and boost their energy, magnetic fields are used exclusively to guide, bend, and focus the beam. This division of labor is dictated by the Lorentz force law, which states that a magnetic field exerts a force perpendicular to both the direction of the magnetic field and the direction of a charged particle's motion. A magnetic field can change the trajectory of a particle, but it does not change its speed or total kinetic energy. Bending a beam of 7 electron-volt protons into a circular trajectory of 27 kilometers requires magnetic fields of unprecedented strength. To achieve this, the LHC relies on 1,232 massive dipole magnets, each measuring 15 meters in length and weighing 35 metric tons. These dipole magnets are distributed throughout the curved arcs of the underground ring, generating an immense uniform magnetic field of up to 8.33 Tesla. For comparison, this is over 100,000 times stronger than the natural magnetic field of planet Earth, and roughly 5 times stronger than the magnetic field of a high-end medical MRI machine. Generating an 8.33 Tesla magnetic field using conventional copper wire electromagnets is physically impossible within the space constraints of the LHC tunnel. A conventional copper coil would require so much electrical current that the electrical resistance would generate millions of watts of waste heat, melting the copper within seconds and consuming the electrical grid of a small nation. The only way to achieve such titanic fields is through the quantum phenomenon of superconductivity. First discovered in 1911 AD by Dutch physicist Heike Kamerlingh-Onnes, certain materials, when cooled below a critical threshold temperature, enter a superconducting state where their electrical resistance drops to absolute, measurable zero. Without electrical resistance, an electric current can circulate indefinitely through a closed coil without generating any heat or losing any energy. The coils inside the LHC's dipole magnets are wound from specialized cables composed of thousands of hair-thin filaments of a niobium-titanium alloy embedded in a pure copper matrix. To maintain their superconducting state under extreme magnetic fields and currents exceeding 12,000 amperes, the niobium-titanium cables must be kept at a temperature of -271.3 degrees Celsius, or just 1.9 Kelvin above absolute zero. At 1.9 Kelvin, the LHC is colder than the background temperature of deep interstellar space, which hovers at 2.7 Kelvin. To achieve this extreme chill, CERN operates the largest and most complex cryogenic infrastructure on Earth. 96 metric tons of liquid helium are pumped into the LHC's vacuum-insulated cryostats. Crucially, at temperatures below 2.17 Kelvin, ordinary liquid helium-4 undergoes a fundamental quantum phase transition, transforming into a superfluid known as helium-2. Superfluid helium possesses zero viscosity, allowing it to penetrate the tiniest microscopic pores of the magnet coils, and exhibits an extraordinary thermal conductivity hundreds of times greater than high-purity copper. This ensures that any heat generated by stray beam particles is instantly wicked away, preventing the magnets from losing their superconducting state. Guiding the beam around the ring is only half the battle. Protons all carry an identical positive electric charge, meaning they violently repel one another through the Coulomb force. Left to their own devices, a bunch of over 100 billion protons would rapidly diffuse, spread out, and collide with the metal walls of the beam pipe within a few milliseconds. To keep the beam confined to a tight, stable trajectory, the LHC utilizes 392 main quadrupole magnets. Quadrupole magnet features for magnetic poles to north and to south ranged in alternating symmetry around the beam pipe. Because of the geometry of the magnetic field lines, a quadrupole magnet acts like an optical lens for charged particles. However, a fundamental theorem of electromagnetism known as Earnshaw's theorem dictates that a quadrupole cannot focus a beam in both the horizontal and vertical directions simultaneously. If a quadrupole focuses the beam horizontally, it automatically defocuses it vertically. To overcome this geometric limitation, accelerator physicists rely on the principle of strong focusing, or alternating gradient focusing. Pioneered in 1952 AD by physicists Ernest Courant, Stanley Livingston, and Hartland Snyder. By placing a horizontally focusing quadrupole immediately followed by a vertically focusing quadrupole, the net optical effect across the sequence is a powerful overall focusing in both horizontal and vertical planes. Further down the line, higher-order multipole magnets such as sextopoles, octopoles, and decapoles act as subatomic corrective lenses. They correct chromatic aberrations caused by slight variations in proton momentum and cancel out chaotic, nonlinear orbital resonances. ensuring the beam remains stable over millions of revolutions around the ring. For these relativistic protons to travel hundreds of millions of kilometers without disruption, they must travel through an environment of absolute nothingness. If a proton traveling at 99.9999991% the speed of light collides with an ordinary atmospheric air molecule, such as nitrogen or oxygen, the collision will instantly knock the proton out of the beam, generating a cascade of secondary radiation and potentially depositing enough heat into a nearby superconducting coil to trigger a magnet quench. To eliminate this hazard, the twin beam pipes of the LHC are evacuated to an ultra-high vacuum, creating an internal pressure of 10 to the power of -10 to 10 to the power of -11 millibars. This is a vacuum more pristine and devoid of matter than the surface of the Moon or the interplanetary space between Earth and Mars. Achieving this vacuum requires a three-tiered pumping system. Primary mechanical pumps rough out the atmosphere. Turbomolecular pumps evacuate the majority of residual gas, and the frigid 1.9 Kelvin walls of the beam pipe act as giant cryopumps, freezing any remaining stray molecules directly onto the metal surface. In addition, the inner walls are lined with a non-evaporable getter coating, a specialized alloy of titanium, zirconium, and vanadium that chemically absorbs and traps stray gas atoms. Inside this ultra-high vacuum environment, the LHC does not maintain a single continuous ring of circulating protons. Instead, the machine operates with two separate parallel beam pipes running side by side through the same shared cryostat structure. In one pipe, a beam circulates clockwise. In the adjacent pipe, an identical beam circulates counterclockwise. Each beam is structured not as a continuous line of charge, but as a train of discrete packets called bunches, under standard high-intensity operating conditions. Each beam consists of up to 2,808 bunches spaced 25 nanoseconds apart, which corresponds to a physical distance of about 7.5 meters between consecutive bunches. Each individual bunch contains approximately 115 billion protons packed into an elongated needle-like volume several centimeters long and less than a millimeter wide, at 4 specific locations around the 27-kilometer circumference. The two counter-rotating beam pipes intersect inside massive underground caverns. These intersection points are the designated collision zones, enclosed by 4 colossal particle detectors, ATLAS, CMS, ALICE, and LHCb, as two opposing bunches approach a collision point. Specialized superconducting quadruple magnets, known as final focus inner triplets, squeeze the transverse profile of the bunches down to an astonishingly microscopic diameter. The beam, which was roughly a millimeter wide throughout the arcs, is compressed down to just a few micrometers thinner than a single strand of human hair and 10 times narrower than a sheet of paper. When two bunches containing 115 billion protons each are forced to pass directly through one another at the intersection point, what actually happens? One might intuitively assume that billions of direct head-on collisions occur simultaneously. In reality, the vast majority of the protons pass straight through each other without touching at all. This occurs because the subatomic world is almost entirely empty space. The physical cross-sectional area of a proton is unimaginably tiny, in the order of 10 to the power of -28 square meters, a unit of area that particle physicists playfully refer to as a barn, because hitting such a minuscule target is like trying to hit the broadside of a barn from miles away. Out of the 230 billion protons passing through one another in a single bunch crossing, only 20 to 60 protons actually collide, because bunch crossings occur 40 million times every second. These 20 to 60 interactions per crossing accumulate into an astonishing collision rate of over 1 billion individual proton collisions every single second inside the heart of each detector. To truly understand what happens during one of these collisions, we must discard the idea of the proton as a solid, hard sphere. When physicists probed the internal structure of the proton in the late 1960s AD at the Stanford Linear Accelerator Center, they discovered that protons are composite particles. A proton is a bound state of 3 fundamental valence particles called quarks, specifically 2 up quarks and 1 down quark. These quarks are bound together by the strong nuclear force, the most powerful fundamental force in nature, mediated by massless gauge bosons called gluons. The theory describing this interaction is quantum chromodynamics. Under the bizarre rules of quantum chromodynamics, The inside of a proton is not a quiet, static arrangement of three quarks. It is a boiling, chaotic quantum cauldron. Gluons are constantly being emitted and reabsorbed, and these gluons frequently fluctuate into virtual quark-antiquark pairs, known as the C-quarks, which exist for a fleeting zeptoscand before annihilating back into gluons. Collectively, the quarks, antiquarks, and gluons inside a proton are referred to as partons. When two ultra-relativistic protons collide at the LHC, the protons, as whole entities, do not collide. Instead, a single parton from one proton sich, as a gluon or an up-quark, undergoes a violent head-on interaction with a single parton from the opposing proton. This process is known in particle physics as hard scattering, because each parton carries only a variable fraction of the proton's total momentum. The exact energy available in each individual parton-parton collision fluctuates from event to event. When two partons carrying substantial fractions of their parent protons, kinetic energy, collide, their individual identities are instantly obliterated in a flash of extreme energy density. At this precise instant of hard scattering, the fundamental physics of the universe is governed by Albert Einstein's most famous equation, E equals mc squared. This equation states that mass and energy are two interchangeable manifestations of the exact same physical reality. Mass is simply concentrated, frozen energy. Energy is liberated, dynamic mass. In our everyday world, converting mass into energy is the basis of nuclear reactors and atomic weapons, where a tiny fraction of nuclear mass is converted into explosive heat and radiation. But a high-energy particle accelerator operates in the exact opposite direction. The LHC takes the immense kinetic energy of moving particles and compresses it into an infinitesimally small volume of space, converting pure kinetic energy into brand new, highly massive matter. For a fraction of a septillionth of a second, the energy density at the collision point mirrors the physical state of the cosmos, just 1 picosecond after the Big Bang. When the ambient temperature of the universe was more than a quadrillion degrees, in this extreme thermodynamic environment, the quantum vacuum is excited, allowing heavy, unstable particles that have not existed in nature since the dawn of time to materialize directly out of the raw energy of the collision. Among the exotic particles created in these collisions are top quarks, the heaviest fundamental particle known. Possessing a mass comparable to an entire atom of gold, W and Z bosons, which mediate the weak nuclear force responsible for radioactive decay, and the legendary Higgs boson. Discovered at CERN in 2012, which represents the excitation of the Higgs field that grants mass to all fundamental elementary particles, these massive exotic particles are extremely unstable. They cannot survive in the low-energy environment of our modern universe. Within a tiny fraction of a yoctosecond 10 to the power of minus 24 seconds, a Higgs boson, or top quark, decays into a cascade of lighter, more stable particles, such as electrons, positrons, muons, photons, and showers of hadrons like pions and kaons. Because the original exotic particles vanish almost instantaneously, no human eye or mechanical sensor can ever observe them directly. Instead, physicists must reconstruct their fleeting existence by tracking, identifying, and measuring the energy and momentum of every single secondary decay product radiating outward from the collision point. To achieve this monumental feat of subatomic archaeology, the collision points are encased inside massive, multi-layered particle detectors. The two general-purpose detectors at the LHC Atlas and CMSR among the most complex instruments ever built. Atlas is 46 meters long, 25 meters high, and weighs 7,000 tons. CMS, while slightly more compact in volume, weighs a staggering 14,000 tons, substantially heavier than the Eiffel Tower owing to its dense iron return yoke and massive superconducting solenoid magnet. Both detectors are built with a nested cylindrical architecture resembling the layers of an onion. Each concentric layer is engineered to detect a specific class of particles and measure a specific physical property, ensuring that almost nothing escapes unrecorded. The innermost layer, positioned mere millimeters from the circulating proton beam pipe, is the silicon tracker. The tracker consists of millions of microscopic silicon pixels and strips, identical in basic operating principle to the digital image sensors found in smartphone cameras, but engineered for extreme radiation, hardness, and sub-nanosecond readout speeds. When a charged particle, such as an electron, muon, or charged pion, tears through the silicon lattice, it ionizes atoms along its path, liberating tiny packets of electric charge. By recording these ionization signals across multiple concentric layers, the tracker charts the precise three-dimensional trajectory of each charged particle with an accuracy of a few micrometers. Surrounding the tracker is a powerful magnetic field generated by the detector's main magnet. Because the Lorentz force bends the trajectories of charged particles in a magnetic field, the tracker measures the curvature of each track. The direction of curvature reveals whether the particle is positively or negatively charged, while the radius of curvature reveals the particle's exact momentum. Straighter tracks correspond to particles carrying higher momentum. Moving outward from the tracker, particles encounter the second layer, the electromagnetic calorimeter. The purpose of a calorimeter is not to track particles gently, but to bring them to a complete, violent stop and absorb their full kinetic energy. The electromagnetic calorimeter is optimized to measure the energy of light. Electromagnetically interacting particles, primarily electrons, positrons, and photons. In CMS, the electromagnetic calorimeter is constructed from 75,000 high-density lead tungstate crystals. Lead tungstate is a transparent synthetic crystalline material that is heavier than iron and denser than zinc. When an energetic electron or photon enters the dense crystal, it triggers an electromagnetic cascade, producing a shower of secondary electrons and positrons that emit flashes of scintillation light. The brightness of the light flash is directly proportional to the total energy of the incoming particle, which is measured by sensitive photodetectors attached to the back of each crystal. The third layer of the onion is the hadronic calorimeter. Composite particles made of quarks and gluons, such as protons, neutrons, and pions, interact via the strong nuclear force and pass straight through the electromagnetic calorimeter without depositing all their energy. The hadronic calorimeter consists of alternating layers of dense absorber plates, such as brass or steel-and active scintillator tiles. When high-energy hadrons strike the heavy atomic nuclei of the absorber plates, they initiate hadronic showers through violent nuclear collisions, as the resulting cascade of secondary particles passes through the plastic scintillator layers. It generates light pulses that reveal the total energy of the original hadron. Beyond the calorimeters lies the fourth and outermost layer, the muon chambers. A muon is the heavier, unstable cousin of the electron, possessing identical electric charge but over 200 times more mass. Because of their heavy mass, muons do not lose energy easily via Bremsstrahlung radiation in the electromagnetic calorimeter. And because they do not interact via the strong force, they penetrate straight through thousands of tons of dense iron and brass calorimeters without stopping. Muons are the only charged particles capable of surviving the journey through the entire inner detector and emerging on the outside. The outermost perimeter of the detector is therefore packed with massive gas-filled ionization chambers and drift tubes known as muon chambers. By measuring the deflection of muon tracks through the outer magnetic return yoke, physicists can identify muons and calculate their momentum with extraordinary precision. There is one crucial class of particles that leaves no trace in any of these detector layers: neutrinos. Neutrinos carry no electric charge and interact with matter exclusively through the weak nuclear force and gravity. A high-energy neutrino produced in a collision can pass straight through the entire detector, through the bedrock of the Earth, and out the other side without interacting with a single atom. How do physicists detect the presence of a particle that is entirely invisible? They rely on one of the most fundamental conservation laws in all of physics: the conservation of momentum. Before the collision takes place, the two opposing protons are traveling purely along the longitudinal axis of the beam pipe. Their initial momentum in the transverse direction, the direction perpendicular to the beam's, strictly zero, because momentum must be conserved in every physical interaction. The vector, sum of the transverse momenta of all particles emerging from the collision, must also equal zero. When the detector sums up the transverse momentum recorded across all its tracker and calorimeter channels, if the total does not balance to zero, it means momentum is missing. This missing transverse energy indicates that an invisible particle, such as a neutrino or, potentially an undiscovered dark matter particle, was created in the collision and escaped into the surrounding rock, carrying away energy and momentum unobserved. Managing the staggering flood of data generated by these collisions represents one of the greatest computing challenges in the modern world. with 40 million bunch crossings occurring every second. Recording the raw electrical signals from all 100 million sensor channels in a detector would generate tens of petabytes of data every single second. This exceeds the total storage and processing capacity of the entire global internet. To handle this data tsunami, detectors employ a sophisticated multi-tiered trigger system. The trigger system acts as an ultra-fast automated filter, discarding the uninteresting, routine collisions and saving only the rare, promising events that might contain new physics. The Level 1 trigger consists of custom-designed, ultra-fast electronic circuits and field-programmable gate arrays built directly into the detector hardware, operating within just 3 microseconds. The Level 1 trigger analyzes course data from the muon chambers and calorimeters to determine whether an event contains high-energy particles or unusual topologies. If an event fails this initial test, the data stored in temporary pipeline buffers is instantly overwritten and lost forever. The Level 1 trigger reduces the event rate from 40 million per second down to roughly 100,000 per second. The surviving events are then forwarded to the high-level trigger, a massive underground server farm containing tens of thousands of commercial processor cores running sophisticated reconstruction software. The high-level trigger fully reconstructs the collision event in real time, performing detailed track fitting and energy clustering. It filters the rate down further, selecting approximately 1,000 to 2,000 high-value events per second to be permanently recorded to disk. Even with this drastic filtering, the LHC produces over 50 petabytes of raw experimental data every year. Storing and analyzing this colossal volume of scientific information is far beyond the capabilities of any single computing facility. To solve this, CERN pioneered the worldwide LHC computing grid, a distributed global network linking over 170 computing centers across more than 40 countries. Through the grid, data is distributed worldwide in real time. Physicists working at universities and research institutes across North America, Europe, Asia, and beyond can access and analyze collision data from their own desks, writing algorithms to search through trillions of recorded interactions for deviations from theoretical predictions. The immense energies concentrated inside the LHC also present profound engineering challenges regarding safety and machine protection. When both beams are circulating at full intensity at 7 teraelectronvolts, the total kinetic energy stored in the beams reaches 360 megajoules per beam. 360 megajoules is equivalent to the kinetic energy of an 800-tune high-speed French TGV passenger train hurtling down the tracks at 150 kilometers per hour, all concentrated into 2 needle-thin beams of protons, narrower than a strand of thread. If an uncontrolled loss of beam guidance were to occur, that concentrated stream of relativistic protons could instantly bore a hole clean through steel beam pipes, puncture cryogenic vessels, and destroy multi-million-dollar magnets. To prevent such a catastrophic event, the LHC is equipped with an emergency beam abort system. If any sensor detects a magnetic anomaly, a loss of cryogenic cooling, or an uncontrolled beam drift, ultra-fast kicker magnets trigger within a fraction of a microsecond. These electromagnets deliver an abrupt magnetic kick that deflects both beams out of the main ring and down to dedicated 700-meter-long extraction tunnels. At the end of each extraction tunnel sits the beam dump. The beam dump is a massive 8-meter-long cylinder composed of high-density graphite blocks, encased in an intricate water-cooled steel jacket and surrounded by nearly 1,000 tons of concrete and iron radiation shielding. As the beam travels down the extraction tunnel, deflecting magnets dilute the beam into a wide, swirling spiral pattern across the face of the graphite block. This spreads the kinetic energy evenly throughout the carbon lattice, absorbing the 360 megajoules of energy and heating the core safely by several hundred degrees without damaging the structure. Beyond beam extraction, the superconducting magnets themselves face the ever-present danger of a magnet quench. A quench occurs when a microscopic region of a superconducting coil warms above 1.9 Kelvin, often due to the stray impact of stray beam particles or mechanical micromovements caused by immense magnetic forces. The moment a tiny section of the cable warms above its critical temperature, it loses its superconductivity and develops ordinary electrical resistance. With 12,000 amperes of current coursing through that point, the resistance causes localized ohmic heating. which rapidly raises the temperature of adjacent sections of the coil. If unchecked, the entire magnetic field collapses within milliseconds, and the gigajoules of magnetic energy stored in the magnet are converted into explosive heat, vaporizing liquid helium and destroying the magnet. To guard against this, the LHC is equipped with a quench protection system. Thousands of high-precision voltage monitors continuously measure the electrical potential. Across every superconducting magnet segment, if a voltage drop of even a few millivolts is detected signaling the birth of electrical resistance, the system instantly triggers high-current heaters embedded throughout the magnet coil. These heaters deliberately quench the entire magnet uniformly, distributing the stored energy across the full 35-ton mass of the magnet and preventing localized burnout. While high-current energy extraction switches shunt the remaining electrical current into massive external dump resistors. The engineering triumphs that make the LHC possible have had profound impacts far beyond the realm of fundamental physics. Particle accelerators are often perceived as esoteric scientific instruments designed solely to answer abstract questions about the origin of the universe. Yet, the technologies developed to build and operate these machines have repeatedly revolutionized human society. In 1989 AD, a British computer scientist named Tim Berners-Lee, working at CERN, invented the World Wide Web as an information-sharing platform to allow particle physicists around the world to collaborate and exchange data across disparate computer networks. The global digital economy that defines modern human civilization owes its existence to the data-sharing needs of particle physics. Today, there are more than 30,000 particle accelerators operating around the world, and only a tiny fraction are used for fundamental physics research. The vast majority operate in medicine, industry, and material science. Linear electron accelerators are standard equipment in modern hospitals, generating targeted high-energy X-ray beams for radiation therapy to destroy malignant tumors. Advanced proton and heavy ion therapy centers use the precise energy deposition characteristics of the Bragg peak to eradicate deep-seated brain and eye tumors while sparing surrounding healthy tissue. Synchrotron light sources giant circular accelerators that accelerate electrons to generate ultra-intense, coherent X-ray beams are used by structural biologists to map the atomic structure of complex proteins, viruses, and cellular receptors. This technology played a foundational role in the rapid design of antiviral medications and vaccines during global health crises. In materials, science, and semiconductor manufacturing, particle accelerators are used for ion implantation, modifying the electrical conductivity of silicon wafers to produce the microprocessors that power modern computers and smartphones. Looking toward the future, the frontier of particle physics continues to push the boundaries of human knowledge and technology. CERN is currently preparing the high-luminosity Large Hadron Collider upgrade, which will increase the collision rate by a factor of 5, generating 10 times more data over the next decade and allowing physicists to study rare quantum processes with unprecedented precision. Beyond the LHC, theoretical physicists and engineers are developing conceptual designs for the future Circular Collider monumental 100-kilometer underground ring capable of reaching collision energies of 100 teraelectronvolts. Concurrently, researchers are pioneering revolutionary acceleration techniques, such as plasma wakefield acceleration, where particles surf on intense waves of ionized plasma, achieving accelerating gradients 1,000 times higher than conventional RF cavities and potentially shrinking kilometer-scale accelerators down to tabletop dimensions. When we reflect upon the journey of a single proton originating from a humble canister of hydrogen gas, pushed by oscillating radio frequency waves, bent by superconducting magnets chilled to the edge of absolute zero, and colliding at the speed of light inside a multi-story cathedral of silicon and steel, we witness the ultimate culmination of human curiosity, scientific rigor, and engineering mastery. Particle accelerators do not merely smash atoms. They peel back the layers of everyday reality, strip away the macroscopic illusions of our classical world, and force the universe to reveal the fundamental rules that govern space, time, and matter. By building the largest machines on Earth to explore the smallest constituents of reality, humanity builds a bridge connecting the subatomic realm to the cosmic dawn, proving that within the heart of a single atom lies the blueprint of the cosmos itself.